Welcome everyone to this webinar. This is the second webinar in the series of OpenMP. The first one was Introduction to OpenMP, and this one we called it Advanced OpenMP or Introduction to OpenMP Part 2, whatever you call it. So I'll go over the slides and you will have a chance to log into Grex as a first step, and I'll tell you when you do that, and then we will start with that so you can have proper resources when I'm talking about different programs, so you will have a hands-on experience in running those programs. So for logistics of this webinar, so if you are using Linux or Mac, so you can use a SSH client built in, so you can use SSH-Y. Just if you want to forward X, we don't need X in this for this presentation, but just in case if you need. And then your username at grex.westgrid.ca, and you should be able to log in because you should have your username and password on WestGrid systems. And if you are using Windows machine, that's okay. You can use any SSH client that you like, as PuTTY or any other thing that you're familiar with, so you can log into Grex. Once you logged into the Grex, you should be able to see a folder called OpenMP-WG-P2-2015. I copied this folder to all the to those who have RSVP to Erin, so you should be able to see this folder under your home directory. If you don't see it for any reason, you can use the command that's a cp-r /global/scratch/workshop/openmp-wg-p2-2015, and then a space dot. It will copy the same folder from global scratch on Grex to your home directory. Okay, so hopefully everybody is in this stage. So you logged into Grex, you see your OpenMP folder, which we are going to work with, or you have copied it. Now it's time to run this command, which is called sh-omp_node.sh. What this command does, it will allocate 4 cores in one of the reserved nodes that we have allocated for this workshop. So it will take a while. It may take maybe a minute or 2 minutes. And you will be able to, and after that couple of minutes, you will be given 1 compute node that you have access to 4 cores. So you will be able to use 4 cores to run your OpenMP codes. So it's better to run it earlier, so it give a few minutes for the system to allocate the resource for you. And if you are using editors, it's recommended to use one of the built-in editors of Linux. That's it's either Vim or VI or Nano or Emacs or whatever that you are familiar with. So it's please just refrain from copying to your Windows or Mac machine and then doing editing and copying back. So it may add some extra characters that you don't want. Seems that we lost connection. We lost people, or? You okay? Okay, so I'll start off with a very brief introduction to what I did in the first presentation or first webinar. So the main motivation for OpenMP was the new modern CPUs, they come with multiple cores. Versus in the past, when you wanted to run your code on a faster machine, you had to wait maybe 6 months or a year to get a new CPU with higher clock speed, and then automatically your code would have been running just faster. But nowadays, that's not the case. The new CPUs, they don't necessarily come with higher speed clock, or even they may get just lower in terms of power, but what they offer you more processing cores. So this year we have, let's say, 4 cores, next year 6 cores, 8 cores, and so on. And on top of that, we have some special devices like GPUs that they have maybe 512 cores or 1,000 cores, or this PHY processors from Intel, which comes with, I don't know, 80 cores, or they have new ones, I believe it's 256 cores and so on. So motivation for OpenMP is that if you want to harness the power of new CPUs, you have to make your code run in parallel. So it's the single image program won't give you any benefit if you spend money on getting new CPUs. And OpenMP is very easy to use. It's supported by major compilers like Intel, GCC, and you can run it in, you can write code in C, C++, and Fortran. And also we talked about that normally the scientific codes, they have some part of code, mostly loops, that they do the bulk of computation. So if you can parallelize that piece of code or that part of code, you will get more speed up in that sense. And OpenMP has three parts. It's one part is, or one component is called compiler directives that we have seen in the previous webinar, which is available on WestGrid.ca website. And I'll go over one of those quickly, which is the most important one, which is related to for loops or do loops in C or Fortran. The second part is library routines that you can use while you're writing your OpenMP code. And the third part is environment variables. And the most frequently used one is one which is called OMP_num threads, that we will use it in this presentation. So I will switch briefly to my terminal. So I'll show you what I mean by that. So it's if you have logged into Grex, you ran that code you got your you're on one of these compute nodes, so you should be able to run this command that I'm just showing you. So it will be my terminal here. I can make it a little bit bigger. So the command that you have to write, it's if you are using bash, you are writing export OMP num threads equals to 4, because in this presentation you are giving only 4 cores. It's better to say OpenMP that you are using only 4 threads, or you have access to only 4 cores. So this one, and now you should be okay. So now, from now on, if you compile your code and if you run your code will run only on 4 cores or using 4 threads. Okay, so switching back to my presentation. As I mentioned before, loops are very important, and it's easier in OpenMP. We will see some advanced concepts today as like tasks or sections, but they have the higher overhead. But loops are easy to parallelize, and you will get more bang your buck in terms of speed up and efficiency. In C++ or C, all the directives will start with # pragma OMP. So all things start with that. And then you will have either parallel for if you have the parallel section and you have only for loop in that parallel section. So you can use the first command, which is OMP parallel for. Or if you have a parallel section, but it's only, but for is one of those one of the components of that section. So you have maybe multiple for loops and so on. So you can write this pragma OMP for before each for loop that you have in C or C++. But if you are a Fortran programmer, so you can use this exclamation mark $sign OMP parallel. So that starts your parallel section. Again, similar to C or C++, if your do loop is the only component of this parallel section, you can write parallel do. But if you have multiple do loops, you can have one parallel section, and within that parallel section, you can have OMP do and OMP end do. In C and C++, each block of OpenMP starts with curly brace, open curly brace, and close it with curly brace. But in Fortran, we have to have this OMP end each time that you want to close the section. So you have OMP parallel do, you have OMP end parallel do, OMP do, OMP end do, and so on. So they have to match. So to get things started, if you have if you like, you can go to the folder that I mentioned, this OpenMP-WG-P2-2015, and you will see two files. One is called OMP_loop_template.c, and the other one is F90. So if you are a C programmer or Fortran programmer, you can edit those. You will see some comments saying that which part you have to put this OpenMP directive. So I'll give you 5 minutes so you can go to that file, find those comments, and try to use one of these directives that I just mentioned. It's pragma OMP parallel 4, or it depends. If you see that for loop is the only component of your parallel section, use that parallel 4. Otherwise, you have to use two different directives. And if you are a C programmer, pick the C.C file, and if you are a Fortran programmer, pick the .F90 one. Yeah, if you comment, if you made your modification, I'll show you the command to compile it. So I will switch to my terminal. So if you are a C programmer, you are using C code, so we will using GCC. So GCC -F OpenMP will tell compiler that you have written some code which has OpenMP directives, and then the file that you have just modified, OMP loop template.c, and the output file will be OMP_loop template. And if you compile this, you should be able to see file which is OMP loop template with no extension. So this is executable code. And remember to have that export command that I showed you before. So I'm running with 4 threads. So if I run this OMP loop template, it will give you the output like this, which shows you thread number 0 will pick up some for loops starting from 0 to 3. So we have 16 iterations, 4 threads, and OpenMP will try to assign as equal amount of iterations to each thread as possible. So the first 4 iterations will be assigned to thread number 0. The second iterations, or the iteration number 5, 6, and 7, and 8 will be assigned to thread number 1. Number 2 and number 3 will pick their own share. But the order of execution, we don't have any control. So threads can run in any order that they like. So next time that you run it, maybe thread 3 gets the first share, finish first quicker, and then print this result. So it doesn't really matter as long as you have this. This time thread 0 finished before thread 1, so you can see thread, oh no, same thing. Yeah, thread 2 and 1, they switch their place. One thing in just the bracket I'm saying, for those who are comfortable with makefile, I have two makefiles for you. One is with capital M for C programs, and one with lowercase m for Fortran programs. I didn't mix those up because I wanted to generate different outputs and so on. So if you want, you can use those makefiles to compile. But I will go over each command that I'm running to make sure that everybody gets the options properly for GCC. So for example, if I have this OMP loop here, so you can see OMP loop. This is the same version that you have, but I've written for you. So if you haven't finished your template file, you can see that OMP loop is the same thing that you were going to say, and then you say make OMP loop. It will compile this OMP loop for you, and then you can run this OMP loop. It's the same thing that you had. Okay, but if you don't know how to run makefile, don't worry. I'll go over the commands as I'm talking, so you shouldn't be worried about that. But if you don't like typing so much, it's easier to use this one. As I said, it's a capital M, which the default one is for C program, and then you can say make-f makefile, and then OMP loop dash. This one it will compile. It will compile the Fortran one. And if you want, just, yeah, that's why, because, yeah. So, let's, okay, so I'll switch back to my slides, if I can. So what you did, you had to add 2 lines because there was, other than for loop, we had some declarations and so on. So we wrote it this pragma OMP parallel default none. Again, default none means that there's tells OMP that don't assume anything about variables, because we will see that variables, because you have multiple threads, variables can be shared among all threads, which we call it shared, or variables can be private per thread. So each thread will have a local copy of that variable. So to give the OpenMP that's okay, don't assume anything about the variables. I will tell you which one is shared and which one is private. So we can say that's default none. So don't assume anything. And then we start writing or declaring our variables. So any variables within that pragma parallel will be private to each thread. And then I wrote this pragma OMP4, which is a directive for OpenMP, telling that the following for loop will be in parallel. And again, as I said, there are 16 iterations, and in our case, we had 4 threads, so each thread picked up 4 iterations. And this is a similar output that you got it from running your code. So that's the same thing, these different threads. And this is the same discussion that I had. It tries to break up evenly among different threads. And we will see another construct called the OMP task for some areas that there's no for loop, but you want to run different sections of code in parallel, so you can use task or section. The other example that we had it in the previous webinar was this dot product of 2 vectors. And we talked about different options and so on. So I don't want to go in details of that, but just a quick overview of that. And we have a serial version here, which is called n.c for C programs and .f90 for Fortran codes. So these are the basic what's called the sequential implementation of this code, which is very simple code. So you have, I show this C code here that has a main file. This is just initialization with some sort of random values, not so much random. It's just the index of for loop, and then it tries to calculate the real value, and then it will calculate using this n dot functions, and it will compare to make sure that the result of n dot function matches with what you calculated theoretically. So this is a serial version. So the section in brown, it's a computation part that we are going to make it parallel, and the green part is initialization. And hopefully, because it happens only once, we don't want to make it parallel, even though you can make it parallel as well in this case, because there is no dependency between different iterations of the same loop. So this is a simple serial code. It's we are using GCC, and this is the n.c, which is the program that you saw in the previous slide. TikTok, there are two versions of TikTok. It's .c and .f90. These are just the utility functions to measure your execution of your program. So they're provided in the same folder that you copied or I copied for you. So you will have TikTok.c and TikTok.f90. And this one is just generate the output. You run it, you will see the execution time. It's about maybe 400ths of a second. Not much. It's just a simple calculation. And if we want to make this code parallel, as I said, we will normally target those loops that are computationally intensive. If you have a loop which runs only once and it doesn't take that much time, maybe it's not it's not worth the effort of you putting to make it parallel. But in this case, we are trying to make this section parallel, which does the actual multiplication of two vectors, the dot product of two vectors, and then storing in the variable called tot. And the first attempt, again, I don't want to go in details of this implementation. There's available on the website, the slides, and the recorded webinar. And in this case, you will see that the first attempt will be writing pragma OMP parallel 4, because we have only for loop in this parallel section. I say default is none, which means that don't assume anything. And I know that this tot variable will be shared. This x and y variables are shared, the same as n. So these are my shared variables. But if you run this code, in the same way you compile it, you say gcc-f openmp, name of your code, and you compile it. You won't see this version in your that folder. This is from the previous example, so you won't see it. So you will see the correct version in your folder. If we do this first attempt of making it parallel, you will see the answer will be wrong, and it will be much slower than single version. And the reason, again, briefly I mentioned, it's about the critical section and the competing threads to update this tot variable. So if you have multiple threads and you have a shared variable, most likely there will be a race condition that everybody will try to update it. And because of there's no guarantee which one does first, answer is wrong. And because of this overhead of each thread trying to access that variable, it takes much longer time. And after a few iterations, again, in the previous webinar, we ended up with a directive. It's called a reduction. Reduction is this type of variables that's the same as shared or private. We have reduction in OpenMP is specifically for this reason. So if you have a value like total that every thread has to update and has to add something to that, you can say that, okay, this tot variable is different. It's not shared, it's not private, but it's type of reduction. And then you will say what type of reduction operation you are going to do on this variable. So you can have multiplication, you can have summation or addition, subtraction, and so on. It's a little bit limited in C. In Fortran, I think you can have average and something like that. But in C, you are basically limited to this basic operations in OpenMP 3.0. But in OpenMP 4, there is an option for user-defined reduction. So you can create your own function which will do the reduction on the operation that, on the variable that you are going to use it. So you can have here the function name instead of just the plus sign or minus sign. This is the version that you have in your local folder. If you want, you can just compile it or use the make file to compile it. So it's called OMP in dot with reduction function. If you want, you can go over the code, run it, and you will see that you will gain a speed up, plus you get correct answer. So correct answer is most important, because if you get the wrong answer, it doesn't matter how fast you get that wrong answer. But in this case, you will get correct answer, and it will be faster because this reduction. So each time that you have this situation, that you have one variable, and that variable tries, it's going to be updated by all threads. So instead of going through the process that we did last time, you can use just directly this reduction directive for OpenMP. So OMP and that reduction, yeah, it's there. If you want, just you compile. You just let me switch my terminal. So this reduction is using TikTok as well. So if you want to compile manually, you have to say -f gcc-f openmp OMP in dot reduction, and then TikTok.c and OMP in dot reduction. OpenMP. Oops, too much MPs. Now you should be able to run this OMP in dot reduction. And then you will see that the answer is correct, because it's two answers, they match. And this is less than what we had for the sequential branch. But again, if you don't want to use makefile, make sure that you are compiling this TikTok.c or TikTok.f90 with your code, because it's using that function to measure the time. So this was just the summary of what we saw in the previous webinar. From now, this is slide number 13. These are basically new material that it's specific for this webinar. It's again built on what we talked about in the previous one. The first thing that you may want to do sometimes is just intervene in the thread synchronization of OpenMP. When you have multiple threads, it's always something that they have to do. It's synchronizing these threads, because at some point these threads should be just wait for each other to finish. Everybody will finish, and the sequential code will resume. So if you remember, again, it's from the previous presentation, in a C code or Fortran code, it starts sequential. It reaches this OMP directives. It spawns threads, let's say 4 threads. It does the calculation, and at the end, these 4 threads, they join, they merge, and then the sequential execution will follow. So you have starting 1 thread, spawning to 4 threads in our example. You can have, I don't know, 10 threads, 12 threads. It depends on how many cores you have in one machine. And then all threads just, they synchronize, they join, and then only 1 thread will resume the execution, and so on. Sometimes if you have, let's say you have multiple for loops in your code, and these for loops are almost, they're independent. So you don't want let's say you have four threads running first for loop, then maybe one thread gets its job done faster than the others. So you don't want that thread to wait for the others, because the next for loop is independent. So you want that thread go and start the next for loop immediately. So then you can use this directive called no wait. So for for loops, you can say that, okay, this is a OMP4, but there's no wait. So if you don't have no wait, OMP will put something called barrier at the end of for loop, which means that all threads has to wait, and then they will go from that point on. But if you say no wait, it means that whoever finishes the first for loop, it's free to start the next for loop. So it's good to go. And sometimes if you have, let's say, some for loops or some kind of parallel, but you have one single command or something after the fact, so you don't care which thread will run that code, so you want to let the threads run at their own pace instead of waiting for each other. So this is something that you may want to do it, but be careful, because sometimes if you put no wait in some wrong places, you may get some wrong answers. So it's better to know what you are doing when you are doing no wait. Seems that there's a question.
So in Fortran we put no wait
at the end.
At the end.
Yeah.
Interesting.
Yeah, it's in Fortran you can see and do no wait, but in C or C++ you put in the beginning of OMP4. So you say that's OMP4 no wait. The other thing that it's sometimes it's possible for when you are doing this scientific calculations is imbalance in your for loop. The for loop that we saw for n dot, it's well behaved. So iterations, they had the same amount of work to do. So let's say the first, if you have 10,000 iterations and you have 4 threads, each one gets 2,500 iterations, and the amount of work is pretty much the same. So not the first 2,500, it's way less than the last 2,500 or so. But this is not the case. Sometimes you get for loops which the load depends on, let's say, index of that for loop. Or sometimes if you're, this is one example that I was working a few years back with a group from power systems here at University of Manitoba. They had this adaptive mesh that they wanted to refine a mesh around those areas that they thought that's the optimization will happen over here, so the optimal value will happen over there. So you had this inconsistent mesh that some parts you have lots of calculations because its mesh is finer, the other one's mesh was coarse, so you didn't have that much calculation. So that's why you have different iterations have different load of work. So in this case, we will see one example here that's just using OpenMP directive with no extra hints will not give you the best option, or will not give you the best speed up that you are expecting. Because default work sharing, we saw that if you have in the previous example 16 iterations, 4 threads, each thread got 4 iterations, and they start from the beginning, and it doesn't matter which one picks the other which iteration, and it assumes that all iterations have the same amount of load. So for this example, instead of going for mesh, I created a simple code, which in this case is the C code. You have the same Fortran code as well. It's called OMP_imbalance. And you can see this the brown rectangle here, which shows the calculation part. It calls a function called the run loop, and the run loops take the index of for loop, and this function has another for loop which runs based on the index that was given. So you can imagine that if we are working on lower index of for loops, the run loop function will finish sooner because the number of iterations is smaller in that loop. But if you go to the higher index of the for loop, the run loop function will run more, and the runtime will be longer. So this is, as I say, just a made-up example to show imbalance nature of a for loop. So if you want, you can go to the same folder. There's a OMP_imbalance_template that you have to just basically write one line of code to make this parallel. So this is the first attempt that we will do it to make it parallel. So I'll give you maybe 5 minutes. Go find that file, try to change it. Again, C or Fortran, it doesn't matter which one you pick. And then I'll show you what I've done, and then we will run to see the result. Again, to compile this code, because it uses this tick-tock functions, you have to include that tick-tock.c or tick-tock.f90 to compile this code. Okay, I'll show you what I did. If I can switch to terminal. So template, imbalance. .c. So it's very simple. We will have to add this pragma OMP parallel for, and it will parallelize this for loop, and it will run it using, let's say, 4 threads or whatever threads. To get some idea, so you may want to just say OMP num thread equals to 1 to make it sequential, and then make it OMP num thread equals to 4, and then to get the 4 threads running on this code. So we will see that you don't get that much efficiency when you are moving from 1 thread to 4 threads. So here I'm just compiling OMP imbalance template.c, including this tick-tock.c, and outputting OMP imbalance template. I also say export OMP num thread equals to 1, and then try to run this OMP imbalance. So it took about 1.96 seconds on Grex. Now I'm just saying for running again. And when you change this OMP num threads, you don't have to recompile or anything. Seems that there's a question.
I think you forgot fopenmp for this compiler.
Okay.
So it will be serial no matter what.
So thank you. So fopenmp export num threads 1, run this code. It should be the same. Yeah. Good. Now making 4 threads. So it's about 2 seconds. If in the ideal scenario, I'm hoping to get half a second because of the 4 times speed up. But let's say how much we get. I'm getting 8.85. It's about 60% less than what I was expecting for. So it's it's not that great. So I have some numbers here to show. So this is our attempt. So we did this OMP parallel for the for loop. And then in this picture, you can see that we have, let's say, 40,000 iterations. And we have 4 threads. Each thread gets 10,000. So the first thread gets first 10,000, second 10,000, and so on and so forth. And you can see that the serial version, it was about 1.96, the same thing, that's around 2 seconds. And with 4 threads, we got 88 or 87 seconds, 0.88 seconds. And instead of getting 4 times the speed up, we got 2.23 speed up, and efficiency is 56%. So it's way lower than what we expected for this simple program. And the reason is, as I mentioned or explained before, different iterations of loop, they don't have the same amount of work. So even though you have 4 threads, the first thread will do just like this, and then will sit idle, waiting for the other 3 threads to finish. The second thread will get a little bit more time, more work to do, but not that much. Third thread will get a little bit more, and the fourth thread will get almost all of the work that it does. And you can see that this lighter color means less work, and darker color means more work. So this is not a fair distribution of tasks among those 4 threads, so that's why we don't have efficiency. And this is not the problem. It's the nature of default work sharing in OpenMP, which divides or tries to divide as equal as possible based on just number of the iterations. However, OpenMP has as a hint, or as again part of a directive, you can give it to OMP parallel for or OMP parallel section, saying that okay, the schedule for this part of the OpenMP code can be this type, and then you can specify the chunk of iterations as well. So I'll go with one concrete example so you can understand what type and chunk means. So I will say the schedule is static. Static means that at compile time it will decide which pieces will get to which thread. So you have 40,000 iterations, and you have 4 threads. If you say M is 10,000, it means that the same as the default load work sharing. So first 10,000 will be given to first thread, second for 10,000 will be given to the second thread, and so on. But you can specify different chunks because you want to get chunks from different part of for loop, because you want to interleave this imbalance work. So you may want to say my M or my chunk is 2,500 instead of 10,000. So then the first 2,500 will be assigned to the thread number 1. The second 2,500 will be assigned to the second thread. And again, when it finishes the number of threads, it will go in the round robin fashion. So if you look at this picture here, you will see that thread 0 gets some part of this low work. Also, it gets some piece of this little bit more work, and the last part, which last time only thread 4 or the 4th thread was doing this. Now it's just each one gets a piece of that hard work that one thread was doing. So you say that okay, this is a static. Again, it will be assigned statically to each thread, but chunk size is not the one that OpenMP decides. Chunk size is what you as a programmer decide, because you know the ins and outs of your program. Okay, so thread 0. So each thread basically will get a piece of different types of work. So low work and high work, just a high amount of work and low amount of work. And if you go to the same code that you did and you try to add this after parallel 4, you add this schedule here and you can run, you will see that you are getting some better speed up and you will get your code run faster. Again, efficiency is 79%, not that much for simple programs, so we can do maybe a little bit better. There are two options. You can either make this chunk size even smaller, so instead of having this thread 0 getting this first 2500, you may get maybe just 250, and then you make more interleave. Of course, there's a trade-off between how many times the threads want to switch between tasks and so on. So that's something that I'll discuss in the next slide or so. But we will try. You can try with a smaller number for chunk, or we can define dynamic. So if you go to if I go to the previous slide, so it's slide number 17. So you have type can be static or can be dynamic. Also, there are some other options like runtime and so on. So I don't want to go in details, but the most important ones are static and dynamic. So in dynamic, so you can see the dynamic is taking chunk size as well, but the behavior is a little bit different. In static, compiler assigns different chunks to different threads in the round-robin fashion. So thread number 1, or the first, thread number 0, or first thread will get first 2500, and then second 2500, a third, and fourth. So it knows which chunks it's going to work on. But in the dynamic, it's runtime. So the first thread will finish the first 2500 iterations, and then it will ask, okay, give me more work to do, and then it will be assigned the next 2500. It will do the work. If it finishes sooner, it will go and ask for another 2500. So you can see the difference is when a thread gets the time to work on that. So there's a less chance for thread to sit idle in the dynamic situation. And if you don't say anything about the chunk size for dynamic, the chunk size will be 1. So it will run one iteration, ask for more work, and so on and so forth. So if you go with this dynamic version here, and you will see that you are getting almost 100% or 96% efficiency, which means that you are close to getting the ideal speed up. So depending on, again, nature of your code, and you know that the nature of code that, because OpenMP doesn't have that knowledge about your code, so you can have some tuning options for your for loop. If you have some imbalanced workload, you can start with some static with different chunk size, or you can go with dynamic. If you see that you are getting better speed up, you can maybe start making this chunk size smaller. Or if you see that it's with dynamic it's getting worse, means that the chunk size is too small, so you may want to increase that one. So that's something that you may consider when you're working in the real-world applications with OpenMP. Okay, so another thing that we can do in OpenMP, it's called conditional. Conditional OpenMP means that sometimes you don't want to go in the hassle, not hassle, but the overhead of creating threads if the number of iterations or number of the things that you are working on is small. So you can say that, okay, make this part parallel if there is some condition. So you can say that, okay, if n is bigger than 10 or 10,000 or whatever that might be, do this parallel section. Otherwise, it will run with using one thread. So you can have an idea of if making more threads makes sense, you can go for that. Otherwise, you can just run with one thread. So you can have here like a pragma OMP parallel, the same thing for Fortran, and then you can have if a statement here saying that, okay, if n is greater than 10. In this case, this code will read one integer from input. If it is greater than 10, you will see that we will get 4 threads running in this for loop. Otherwise, it will run only one loop. Okay. The other thing that I'm going to talk today is non-loop parallelism, but sometimes, most of the time, you have loops in your code and you want to make it parallel. So you want to make use of all the cores available to make or you finish your job faster or run your code quickly. But sometimes you have hard to parallelize code that doesn't fit in that OMP4, OMP do construct. For example, you have a while loop, which doesn't have that nice feature of how many times you are you have to iterate and so on. So those are the hard to parallelize code that you can't do with that standard constructs like OMP4 or OMP do. Then you have option in OpenMP that you can create sections. So sections, you can create parallel sections of your code, and those sections will run concurrently by different threads. And you can do whatever you want in those sections. You can write another for loop and so on in that sections, or you write, as I said, a while loop, or do some calculations on different functions. So even though the functions, you don't have iterations, but maybe you have 2 or 3 different functions that it takes a while to calculate, and they are independent, so you want to run them concurrently, so you can create sections. So sections should be within OMP parallel. So you have a OMP parallel as a parent. Then you have the sections construct, and then within sections you have the sections construct, and then within sections you have one or more section construct that you want to run it. The same as combining parallel for or parallel do. So if sections is the only component of your parallel section, you can say OMP parallel sections. Okay, so that's some shortcut if you want. And this different OMP section, you have to have, these are static, so you have to know how many of these sections you have in your code. So you can have, in this case, I have 2 sections here. There's one example in your folder. It's called the OMP_section.c. If you want to go in that code, you will see that there's a C code, again, the same as a Fortran code. We have parallel sections, and parallel sections has only 2 section directives, and one is calling hello1 from thread and hello2 from another thread. So we will see which thread is running which part of the code. I'll switch to my terminal. OMP section.c. So you can see that it's a simple code. OMP sections has 2 section constructs, and it just says hello from 1 and 2. So I'm just compiling if OpenMP OMP section.c, and output will be in OpenMP section. So, and remember that I have this export command. So I have 4 threads, and then I'm running this code. So in this case, the first time that I ran, the thread number 0 and thread number 2 picked up the section and ran it. Second time, thread number 0 and 1 ran those 2 sections, so it doesn't matter. So it will pick one of these 4 sections. Oh, sorry, 4 threads will pick the first section. The second one will pick the second one, and so on. So you can have maybe 4 sections, and each one will be picked up by one thread. It's non-deterministic, and it's possible that the first thread finishes before the last thread gets assigned, so one thread can do multiple jobs. So let's say OpenMP section. So if I copy, let's say for YY. So if I copy, now I have 4 sections and I have 4 threads. I'm hoping that each thread will pick one, but you can see that, oh, this one, each one pick one. But sometimes one thread could take more than one section. Okay, so the question was assigning threads to sections are deterministic or not? Yes, it is. It's It's non-deterministic, so you don't know which thread will run which section. And as I mentioned, sometimes one thread can run more than one section, depending on which one finishes first. And the last thing that I want to talk is about tasks. These are the generalized version of section. It's introduced in OpenMP 3.0, and they added so many new features in OpenMP 4.0. We will see that, let's say, the dependency between tasks and you aggregating tasks and so on. It's in OpenMP 4, not in OpenMP 3. And they try to solve the problems that we had with sections. One was just the static nature of section directive. So instead of having the static number of sections in your code, you can generate tasks on the fly. So you can have a while loop, and then in the while loop you can create tasks, and each task will be assigned to one thread and run it. Okay, so they will try to reduce that static nature of sections. This directive that we are going to use is again hashtag pragmaOMP, which we have it for all the directives of OpenMP, and then you can have this task keyword here, and it will create one task for you. And task is almost a self-contained package which will be handled by OpenMP. It will be assigned to a thread, but the running time or when this task will be started is non-deterministic. So it may start immediately, but it may wait for some time. So it has its own queue of tasks, so that will be put in. So it's a little bit different than section. And to use tasks, it's better to use this pragmaOMP single before starting any task. Otherwise, each thread will start task. So I'll show you this example so you can understand better what I'm talking. So again, everything should be in OMP parallel section. So that's the default. Everything should be in the parallel section of OpenMP. And if you have this OMP parallel here, it's normally better to put OMP single, so only one thread will do this part. And then that thread by itself, when it goes through this line of code, whenever it reaches this OMP task, it will create a task. As I said, imagine that it's a package, it's a box with all the data, everything is required, and it will give to the OpenMP to run. Okay, so the first thread that goes through this line of code doesn't run the task, it just creates the task. And then another task, including the one that created the task, could run the task itself. Okay, so it's a little bit different concept than section that threads ran in the section parts. So here, one thread will go through here. It will, let's say, the first thread, because it's single, it will print this line. It will reach this OMP task. What it does, it creates a task. It doesn't run any code. It creates a task, gives to OpenMP, moves to the next one. It creates another task, gives to the OpenMP, and then finishes. If it finishes the if it finishes the work of creating tasks faster, it will pick one of those tasks and run whatever the task is required to do it. Okay, so let me run this code so we can maybe have better understanding of which thread is doing that. So if you go to the same folder, you have OMP task.c. This is the simple program to create a task. So I have this parallel here. I also have single. Oh, I didn't switch. Sorry. So I have to switch my to terminal. Okay. So you can see on the screen, and also if you open your version that it's on the home directory, you can see that OMP parallel here, OMP single here. If you recall, OMP single means that only one thread, doesn't matter which one, only one thread will run the following code. So the following code means printing the thread number and then creating tasks. So if I run this code, you will see that they will be printed, there will be thread number will be printed, and then there will be two another thread numbers that they are doing the task. And they could be different, they could be the same. So let's gcc-f openmp omp task.c -o omp task. OMP task. So you can see that thread 1 is creating task, and thread 2 and 3, they ran tasks. Okay, so the thread 1 was the one that was creating the task, and thread number 2 and 3, they did basically the body of tasks. So if I run again, you may get different things here, just 2 and 0. And sometimes you will get the same task that is creating tasks. You can see hello from, that's the same, none in this case. Yeah, but it's possible. Okay, so I'll show you the code again one more time. So one thread goes through this OMP single, then it runs this printf command, and then it goes through OMP task, so it creates the task. Task is a package. It seems that it's a box with everything that you need, every data, everything, and it gives to OpenMP to run. So OpenMP has its own facility to run these tasks. Then moves to the next second statement of creating task, creates another task, and it finishes the job. And the other threads will pick up the task and then run it. Yes?
Should there be always more threads than tasks in the code?
No, not necessarily. It's better to have it, but if you have only one thread, let's say, it will create those tasks, and then it will try to run one at a time. So OpenMP will assign each task to one thread. So if you want to see what happens if you remove the single command, go to the same code and try to comment out that pragma OMP single line to see what happens. So I'll do the same thing with you. So I'll go to first share this terminal. Try to guess before running the code to see if you understand the concept of the task. Try to see what do you think is going to happen. So I'm going to run this. So if you guessed what happened, that you will end up with 8 tasks. You were right. So if you remove single, so each thread that goes through the tasks, it will create tasks, and then it will run later on. So each, let's say, you can see here, thread 0 is creating tasks, thread 1 is creating tasks, thread 2 is creating tasks, thread 3 is creating. So every thread will create a task, and then those tasks will be queued, and then will be run by the same number of threads. So you can see that hello 1 is from thread 0, hello 2 is from thread 0, and thread 0, it seems that it's taking most of the tasks to run. So, and you can have most of the tasks were run by thread 0, and we have some from thread 1, 2, and 3. Okay, so it's important to have that single because you don't want to create so many tasks. You want to create only the number of tasks that you think is appropriate, and then threads will run those tasks in parallel. Okay, so that's the important piece here that you have done. So as I mentioned, tasks are independent unit of work. Box or the package that has everything, it's handled by OpenMP. They have their own scheduling. You don't know when they are going to start, nor it could happen right away, or they could wait for some time before they start running. And each task will be assigned to one thread to run. So if you have, as Gregory asked, that if you have less threads than number of tasks, so maybe one thread will pick up the more tasks to do it. And tasks are good for, as I said, hard to parallelize problems. One example is for, let's say, traversing a linked list or tree. So if you are not familiar with binary trees or linked lists, that's no problem. Just I have a small picture here in the corner showing a binary search tree, which normally happens if you have lots of data and you want to have a fast searching. So you normally assign it or put it in a tree fashion. It's a binary tree fashion. What you can do, let's say in this example, you can create a task to search for the, let's say, left part of this tree and another one for the right part of the tree and so on. Even, as I said, depending on the application, maybe it's not a good application because the binary search tree has special features that make it possible to search quickly, so you don't have to even go to different branches to find it. But anyhow, the concept is you have different parts, you can assign it to different tasks, and it doesn't have to be for loop or do loop or whatever, so you can create anything you like. There's one example in your folder. It's a C code. It's not Fortran code. I didn't know how to write, or even it's possible to write a linked list in Fortran, so I couldn't write it. So I wrote just one example in C, which is a linked list, and it gives each links to different tasks to traverse that linked list. So if you want to play with that, you can go to the same folder. It's called OMP_task2. It has that linked list version. And the last example, that if you, I think we have some time to do it. Let's see. Yeah, we have. So you have a code which is called OMP task fun template. Oops. Don't look at that. So if try to write this program which randomly prints either a race car or a car race. Okay, so you are going to use 2 threads to do this, and template is here is just a way that you have to put tasks in correct position. So I just basically wrote the code for you. So you just open the file and put those OMP directives in the correct place. And if you run one or twice, sometimes you'll get a race car, sometimes you'll get a car race. So depending on which thread picks which task to run. So I'll share my screen. So basically, you have to just put OMP parallel, OMP single, and then 2 OMP tasks. Is there any question?
I found it really hard to get undeterministic behavior in Fortran.
Yeah, it's hard in Fortran. I don't know why. That's right.
I got only one a race car over like 15 a car race.
Yeah. I don't know. That's right. I tried that one myself and I realized. But in C, you can get pretty quickly that a race car. Oh, no, maybe. A race car, yeah. So when you are working with threads, please don't assume any dependency or any deterministics between which one will run first or second, unless you have a specific, they call it barrier or synchronization yourself. So that's maybe beauty of having multi-threaded, so you don't have any control on that. But at the same time, you know that those are doing their own job. So as long as you split your job and properly among threads, you will get correct results. So in this case, simple program here. We have parallel, single. Oh, sorry. So this one doesn't have any slides. So I'll have to show my code, which is nothing really fancy. It just... So I have this OMP parallel, then OMP single because I want one thread to create different tasks. I put print A first because I want A to appear before car race or race car. So that has to be deterministic. It has to be before all that. And then I create 2 tasks, and the order of execution of those 2 tasks are non-deterministic. So sometimes car will get printed first, sometimes race get printed first, so you will get a car race or a race car. Yes?
But if you wanted to print a new line after that and make sure that that's the last thing, so how do you make the end of that second task?
The task should be the same block. That's I believe it should be like this and this like. So this is one task.
So it would just be before that one statement or that one block, and after that is sequential code.
Right, exactly. So the question is how can we define a block of tasks? So the block of task is defined the same way that we define the other blocks, using curly braces in C. And then in Fortran, you make this end task. So it's easy in Fortran, but in C, you start curly brace. You put everything that you want to run as one task within that curly braces, and everything outside of that will be just a sequential execution. The other thing that I didn't mention, we are almost running out of time, so I'll give some few minutes for questions. So you can synchronize this task. So you can have a task wait command in OpenMP saying that, okay, even though you have many tasks doing different things, I want all the tasks to synchronize at this place. Let's say you say that you want to say a car race or a race car is fun to watch, for example. If you want to say to make sure that is fun to watch statement prints after all tasks, you have to wait for previous tasks to finish and then write your code. So you may want to try this one. It's called task wait. And then you can, there's a cheat sheet PDF link in the presentation at the last slide, so you can have access to that. It's good to have it handy when you are writing your OpenMP code. Okay, so, and the last slide is not a slide about one little bit more complex program using task, again, related to processing a linked list. So you can have here the same The left-hand side describes exactly what happens. A team of threads is created at OpenMP parallel. So you have, if you have 4 threads get created in the first line. Then you have the single line, so only one thread will go through and then will run the following code. So it will get the head of linked lists. Again, if you are not familiar with linked lists, that's totally fine. It just gives you the idea of how we can distribute different computation among different tasks. So the first one will get something. This is the head of linked list, so you can imagine anything can happen. And then we'll have a while loop. And within that while loop, I'm just creating task when I'm just passing by open task. So that one thread that had a chance to go through it, it will create thread, and then it will pass it this P, which was reading from the head of the linked list. You see here, it's another thing is called the first private. The same thing that we had shared, private, reduction, and so on. We have something that's called the first private, which means that when you are entering this task, P will take the value of the value of P is defined, and it's defined, and what the value is the value that it has before starting this parallel section, before starting this task. So the first time that I'm going through this OMP task, P will be the head of linked list. So this P will be the head of linked list. The second time, I'm just moving P to the next link, and then next time that I'm creating task, P will get new value and so on. So again, the first private is something that you will find it handy when you are working with tasks, because when you are creating a task, you want to initialize your data. You don't want to send something undefined to tasks to start with. As I said, you can read through this left side, exactly explains what's happening in the right side. Again, it doesn't matter, it's a linked list or whatever, it's as long as you have some sort of computation which doesn't fit properly to the OpenMP for loop or do loop, you can do it with tasks. And again, in OpenMP4, we have so many different options that if you want, you can read it, because this is just the beginning of your OpenMP journey to make your code faster to run on WestGrid or any other Compute Canada website. This is just a conclusion. I'll make it quick so you have some time for questions. So we saw that OpenMP is relatively easy to work with. It's just simple constructs, directives. You put it in your compiler, you compile your code, and automatically it picks up the threads and it will use multiple cores. You have this OMP num threads, which controls how many threads you can use on particular machine. And in addition to loop parallelization, which it's recommended to use because it has low overhead, but OpenMP offers some constructs like tasks or sections for those corner cases, which doesn't fit properly in the OpenMP for or do loops. And also, if you try something and you couldn't figure out what's going on or how to convert your serial code to OpenMP, just send us an email to support@westgrid.ca, and we will be willing to or more than happy to help you. Sit down or have some video conference or whatever it's possible to go through the code and then come up with some solution that will make your code faster on Compute Canada resources. And these are some useful links. I put the link for previous webinar here, Introduction to OpenMP. You click it, you will find the slides as well as the, I think, recorded webinar. And these are two cheat sheets that I mentioned for OpenMP 3 or 3.1. This is for C programs, and this is for Fortran. It's better to have one copy handy so you can have different syntax and so on. So by that note, I'm done. So if you have any questions, I'll be more than happy to answer them. No questions in the chat list? Anybody is there in? Okay. Okay, so if we don't have any questions, if I can go. What happened to my machine? Okay. Okay, it's time 2:24 Central Time and 12. Yes, there's one
question. Yeah.
Okay.
Is there any WestGrid systems that offer OpenCL yet?
OpenCL?
Yes.
What's OpenCL? Sorry.
This is like.
Oh, okay. Yeah, OpenCL. It's one system in Calgary. It's called the Parallel machine, parallel.westgrid.ca. It has, I don't know how many GPUs it has, but it has many GPUs that you can run your code on. Okay, so you can either use OpenCL or you can use OpenMP4 features to run your code on CUDA or on NVIDIA machines, which I think ours is Kepler or something. So you can go to the quick start guide of Parallel machine and you will see how, but you have to have a separate account on Parallel machine to use those. No more? Okay. So thank you, everybody, and have a good summer. Hopefully, we'll see you sometime soon, virtually or in person.